The idea behind this work starts from an observation that several methods for delta G calculation are parameterized with respect to the free energy difference between the folded and wild type protein. But this is not really a free energy for a process, since mass is not conserved if you just consider these two terms. In order to have a proper free energy, you have also to consider the free energy difference between the unfolded states of the two proteins. And free energy is defined for closed system where mass is conserved. So we thought that this is an imprecision. And many methods that we call potential-like are parameterized this way, namely most force field, protein language models, and also some specialized tools such as Pythia, which is a graph neural network to predict the effect of mutational scan on a protein. So, if one considers the correct process, taking into account also the differences in free energy between the unfolded states, one can make the approximation, which is not so drastic, of considering that the free energy difference between the unfolded state of the wild type and mutated protein is just the difference in free energy between the amino acid involved in the mutation. If one does that, it is possible to derive this contribution in a data-driven way by fitting a 21 element linear combination to some training and test data, which is exactly what we did to derive our data-driven mass balance correction. We tested it on several methods, like the IF1 protein language model, the FoldX force field, and Pythia graph neural network, where we find substantial improvement in their performance, as it is shown in figure 2. We also tested the performance for methods that already consider the amino acid involved in the mutation among their features, such as stability oracle and DDGAN 3D, and this method either do not improve or get worse because of overcounting. After we verified this condition, we also noticed that our data-driven mass-based correction correlate very, very strongly with a Pearson correlation coefficient of more than 90% with the Rose scale that has been experimentally derived in the 80s and that represents the change in the entropy of solvation among a mutation in a protein. If one So it is possible to derive the new mass balance approximation, which is just two parameters, involves just two parameters, namely the answer of the original method and the difference between the Rose scale values for the two amino acids involved in the mutation. If one does that, get gets basically the same result, and we tested it on the giga data set and also on more than 40 methods that have been recently tested in a Nature Machine Intelligence paper by Reeves and Kanamurthy. The results for these 48 methods is shown in figure 3, where basically all the methods which are not mass balanced aware get substantial improvement, even sometimes close to 20% more in Pearson correlation coefficient. And while methods that are already aware of the stoichiometry of the mutation either do not gain anything or get worse performance. It is also interesting to note that the PISA method retrofitted with our correction gets basically state-of-the-art performance on par on methods such